Okay, so I am going to speak about shape modeling. It's talking in two parts. I first give a brief overview about shape reconstructing Juno, and then I will talk about Juno and how we model it from the ALMA situation. So first the overview. So ADAM is an acronym for all data asteroid modeling, and the idea is that we have a non-convex and non-star shape representations, and we can combine basically all these pieces of data, namely adaptive optics, range stopper, thermometry, and of course light curves, the one coherent shape solution. Okay. So I use gradient-based optimization. So this is the flowchart. So we start with. Oops. Yeah. So we start with shape parameters, and we generate surface mesh, and then we have a observation-dependent projection operator camera frame, and then we do two-dimensional projection to a plane, and then we do the two-dimensional Fourier transform, and we can combine the instrument-dependent points per function, and we have observation and data, and then we convert the observations or data to Fourier domain, and then we do optimization here, and then we have several regularization parameters, of course. And then we update parameters and start again. So the main important feature is the Fourier transform. Here we do all shape building in the Fourier domain. So why Fourier transform? There are several benefits. First is that we don't need to extract boundary contours in images, I mean, like any discrete images, and we don't have any problem with pixel size because the pixel size corresponds to the maximum frequency present in the images. And of course, we have another thing is that one pixel, one local feature is converted to a global feature on the Fourier plane, so we don't get stuck in the local minimums so easily. And of course, we can include the points per function easily, and we can do the convolution operation during the shape optimization. So let's see a couple of examples before we move into Juno. So here is first adaptive optics shape cluster Daphne. So we have 19 near-infrared adaptive optics images and several light curves, and the pixel size in the images is like 10 kilometers. So here is two different shape solutions. The idea is that when we use two different shape models, we can do something similar to Markov-Chain integral. The first requirement is that if you have consistent data, then all the shape representations should give something similar. So you see that the main features of these both models are similar. There are some minor differences in here, but the shape is both solutions are ultimately the same. So here are example of it. here we have adaptive images, and we have two corresponding model fits here. We see that even the non-convex features here are present in the model. And here also there, and there is some non-convex features, and also here. Then the different example, we use range Doppler images. We have a small near asteroid 2070. As you well know, Doppler range Doppler radar will resolve asteroid in range and line of sight velocity, and we have radar images from Arecibo and Costone. We do medium resolution here, and we assume that the point square function is delta function because we don't know what the true point square function is. So here we have reconstructed model. We see that there are several non-convex features, and of course, then important thing is that the radar range Doppler is many to one mapping, so it's very hard to say what model is correct. So here are some example fits to the radar data. We see that the features are very nicely visible here, and here are some features there. Of course, we are mainly interested in the boundary, the features that are inside inside the image are not so important when we want to do that medium scale reconstruction. Here are some other images. You can see that some of the features are very nicely produced in the model. And of course, the important thing is that this fast reconstruction. This model was calculated in 20 minutes. Now the main part, so thermal modeling or thermophysical modeling. So first, the interferometry. Just to remind you what the ALMA does. So here we have antenna positions on Earth, and then each antenna pair or baseline gives one sample on the Fourier plane. So we have a sparse example Fourier plane. So mathematically, what happens here, we have a true brightness distribution, and then we have a point square function which corresponds to Fourier transform of this. So what we get is a so-called dirty image. Here are some sample dirty images of Juno. This is real data from ALMA. So here we see the actual shape, and then everything else is due to sparsely incomplete Fourier samples. For thermal modeling or physical model, we use a simple model, we ignore infrared beaming, and we ignore also secondary reflections and radiation from other parts of the asteroid. And we do just the usual assumptions so that we can calculate the temperature per facet easily. So the usual heat diffusion equation and then the usual boundary conditions here. So F is the insulation. So we can solve this using, we can use finite difference. We usually solve this using finite difference method, but we can also solve this using fast Fourier transform because the insulation of the surface element is periodic. So we can expand the insulation in Fourier series, and we of course have to assume that the mean temperature changes are small compared to the mean temperature, so that there are no large variations. And if we expand the insulation in Fourier series, the dn are Fourier coefficients, then we get radiated flux in this form. And we can calculate the derivatives also analytically, so we don't have to do finite difference. So here, of course, we have some disagreement with this method compared to finite difference solution. In the vertical axis is temperature, and here is the angle between surface normal and sun's direction. So if you have a low thermal inertia, then the disagreement A is 20 degrees. But if you have a thermal inertia of 600, then the difference is only 4 degrees here. Now the idea for shape reconstruction is that this simple model is enough because the most of the information is on the boundary. And of course, we can use sophisticated models, but we have to pay for that. So, Juno, what we have is a large membered asteroid, and the diameter is approximately 250 kilometers, and we have a very low thermal inertia, 5. And what we do on variable data, we use light curves, and then we use science verification data from ALMA. We have 10 observations. Angular resolution is not very good, but we can still do the shape reconstruction. And of course, another problem is that the viewing views are restricted to the northern hemisphere, so the northern hemisphere is not very well resolved. So here is the actual data. These are deconvolved images from ALMA, and we use these to reconstruct the shape. So what we do here, we don't use the actual images. We could, of course, but we use the calibrated Fourier or calibrated visibility data from the instrument. And of course, there's problem with the phase errors, but in this case, the phase errors did not affect shape solution, so we ignored those. So here's the reconstructed model of Juno. We see that there are, the shape is non-spherical. There are some interesting features in the images. And now shows the model with the images. We see that the fit is not perfect. Here is the model fits, but there are some very similar features here and here. And of course, the data resolution is like 60 kilometers, so we really don't know if we can do it better. So, of course, the question is how reliable this model is. We have a model that fits the data, but we don't know if it is actually the Juno. So, what we do with some other data, we have adaptive images from Keck and also sphere data from very large telescope. Very large telescope. So what we do is we construct the model from these images. So the adaptive optics model is here bottom, and the previous ALMA model is here. So we see that the large-scale features are similar. There are, of course, some details present in the AO model that's not in ALMA model, but large-scale agreement is quite good. So here is also the bottom row is the A model compared to the ALMA data. And the rest of the images. So we see that even we have a better resolution AO model, it really doesn't give any better fit to the ALMA data. There are, of course, some minor details here that are not present in the ALMA model, but the shapes are very similar. So, the conclusions, we see that we can use ALMA data for shape reconstruction. And of course, the resolution is still not very good, but it seems that in its full capacity, we will get to the 5 milliseconds, and that will be very good. And finally, differences. So the stuff about Juno, the submutated to A at A, via the sphere and ALMA-based shape reconstruction. And then there are 2 other articles about the ADAM, and this article is more application-oriented, and this published in the inverse progress is more about theory, about shape reconstruction. So, thank you.
If you take your shape model and convolve it with the clean beam that they would have used at ALMA and take the difference, I mean, is that a way of assessing how well things look? It's a little hard to tell exactly how well you're matching the ALMA data with the model if you just compare the model and the image.
Yeah, the problem is that basically we can do that, but the problem is that the convolution, it's not very transparent. We really don't know what happens when we do the convolution. So that's why we use the raw data. So we really don't know how reliable the compound data actually is. So that's why we do the.
Well, I agree that using the raw data is absolutely the right way to do this. I was just looking for a way to, assess how, whether your model and that image are really consistent with each other. Really, all you can tell from this is they have about the right shape and so on. It would be interesting to look, let's say, more quantitatively at the residuals in a space like that we can understand.
Yeah, I know this is a very general problem because the question is how we can compare two models. So it's a very it's a very problematic question, but of course that's the one way to do it. Yeah.
One more questions, so we're a little late, but it's okay. No, there are first questions here. So Alberto is first.
Assume to have the mass of this object.
Okay.
Let's assume that we have a precise determination of the mass. Okay. Then we want to derive the density. What is the difference between if you consider the volume represented by this shape and the volume of a circumscribed triaxial ellipse is much simpler, and you make a big error or not?
The volume of this model is the diameter of this model is 245, if I remember correctly. So it is yeah, 250 diameter. I think, yeah, diameter is 250, 245, if I remember correctly.
I think the question is more, could you tell us, maybe not now, but in future, what is the error of comparing your model, the volume of your model, compared to the equivalent triaxial ellipsoid? This is because Gaia will publish triaxial ellipsoids. And so it's very interesting to know what's the error.
Yes, I think, yeah, it's possible to calculate it, but I might done it now, but it's possible, of course.
There's Matti, more questions, two or three more questions.
Yeah, really impressive work.
Thank you.
There's two problems I have with your thermal modeling, though. One you mentioned yourself is your assumption that the temperature amplitude is low compared to the mean temperature. That's really not the case for Juno.
Yeah.
So I'd encourage you to just run it with a finite difference model instead of the Fourier as simplification.
Yeah, the idea is that even the difference is large. The boundary of the asteroid is the boundary curve of the asteroid.
Well, one of your boundaries is where the sun rises, right? That's where the difference is the biggest.
Yeah, but
High.
yeah. So the difference is large, but because we are interested in relative differences, and phase angle is like 20 degrees, I think. So there is not really big difference because the larger difference is here. So it's the night side of the asteroid, but for these ALMA images, we are in these regions here, so difference is not that great. And even if we can still the boundary is the most important feature.
Yeah, in fact, I have another question that might actually be nastier, sorry. Is you make one implicit assumption that I think all of us in the room make, and that is that the emission is from the surface. That's a good assumption in the mid-infrared, but it's a bad assumption in the sub-millimeter where ALMA observes.
Yeah.
Asteroid material is relatively transparent at those wavelengths. And there's a paper by Chamberlain et al. 2009, where they even observed Juno at 870 microns. And they conclude that they see significant evidence that the emission is actually from below the diurnal heat wave even. I'm not sure if this is a problem for you at all, but it's definitely something you want to think about.
Yeah, it's a. Of course, we cannot really know how deep radiation is bad, subsurface or surface. But of course, I'm more interested in shape modeling. So this just something to show that we can do shape from the thermal data. Of course, we could also include subsurface in the model, but it would really be shape model then.
We have one more question here from Javier.
I wonder what are the limits of ALMA and these techniques. I mean, how many asteroids and what size or where in the main belt are we going to be able to see shape models like this?
Well, I'm not the right person to answer that because I just use the ALMA data, so I really don't know how well ALMA is going to perform.
We're 2 more minutes, so I have a question myself. If there's no more questions. All right. So I would like to ask you if this technique, but I assume it is, could be applied to medium interferometry, in particular MIDI from the VLTI. MIDI is N-band and is measuring visibilities. And there's an upcoming instrument that is Matisse, that is built at our observatory. It will go on the sky in 2 years, and it will measure visibilities using the 4 telescopes. And so maybe this could be interesting for you.
Yeah, probably. I think we could use the data. Of course, we have a mathematical model, then I think we can use that. Yeah.
And very quickly, I think Juno has many occultations, so occultation data. So it would be probably interesting to check, or let's say, compare your model with the occultation.
Yeah, we compare it to the occultation. In fact, it's going to be in this first article. There is occultation data. It shows that the occultation data agrees with the model very nicely.
Okay. No more questions, so we can move on. Thank you, Matti. Thank you. Very good work. So next. So next talk is going to be given by Joseph Hanus. He's actually uploading his talk, and we keep talking about shapes. And so I don't remember his title out of the top of my head, but I know what it's talking about. So he's going to talk about the importance of thank you, effects of shape uncertainties in thermal modeling with revised WISE uncertainties.
Okay, in today's talk, I'd like to talk about how we can derive reliable thermal inertia values based on inputs from WISE, namely the thermal infrared data, and second input, the convex shape models, and their side rotational periods and orientation of the spin axis. And we would like to derive the thermal inertias by the thermophysical model of Lagros and the implementation of Marco-Delbo. And I'd like to also show our investigation of the role of the shape model and polar orientation uncertainties that affect or how can they affect the thermophysical properties we derive. And finally, I will also discuss the quality of the WISE data namely the accuracy and some systematics reported in the literature. So thanks to Marco and the other talks, most of my introductions are also already said. So just briefly, I'd like to show you the main difference between the thermal models and the thermophysical models. There are two main thermal models, namely the standard thermal model and the Tenerife Asteroid thermal model. And okay, they are both based on the equilibrium between the absorption and the emission, and they both include the magic normalization factor called beaming parameter, which for the standard thermal model is calibrated thanks to stellar occultations, measurements of Pallas and Vesta, Ceres and Pallas, and is set to this value. However, it does not work, or this value is not correct for smaller asteroids. So the main difference between these two models is that the NITEM does not use this parameter as fixed, but optimizes that as well. And both models assume spherical non-rotating objects, and if we have a thermal light curve, it's just simply averaged to the mean value. And these models, together with assumed H and G values, give us diameters and albedos. And it's the best model we can use if we do not know any other information about the physical parameters of the asteroid. So it's not surprising that the albedos from WISE were determined by the NITEM model. On the other hand, the thermophysical model aims to use more realistic shapes and compute the temperature profile on the surface for a set of parameters like size, albedo, surface roughness, and thermal inertia. And they as well assume the H and G values. And from the temperature map, we can easily determine the thermal infrared flux for a given wavelength and compare it then with observations. So the heat diffusion equation is solved in the surface layer of the asteroid, and we need to thermalize the object, and also we can include the initial rotation phase of the object into the optimization if necessary. So there are two main thermophysical properties. One is thermal inertia. So just briefly, it's the combination of density, thermoconductivity, and heat capacity. And it has many useful implications for the Yarkovsky effect. It tells us something about the regolith grain size. And typical values are very small for big asteroids or Trojans and TNOs, and they are much larger for smaller asteroids. There is not much known about the middle-sized asteroids. And this is the effect of the thermal inertia. These are thermal light curves for the same asteroid with the same parameters, but the thermal inertia is changed. So you see that if you increase the thermal inertia, you decrease the thermal flux. You also slightly shift the maximum of the flux with respect to each other. And the second parameter is the surface roughness. We use a simple model of the semi-spherical crater with described by two parameters. One is opening angle, and the second one is the surface ratio covered by this crater on each facet. So the shape model is basically a polyhedron divided into facets, and each facet has this crater. And there is an alternative parameterization called sometimes Hopkins mean slow, which is just one parameter, but it's ambiguous. And in the crater, we include shadowing and self-heating, and also there are basically two things how to deal with them. We can use the analytical Lagrange approximation, which seems to be reasonable and gives us a lot of computation time compared to the numerical model where we solve the heat diffusion in the crater. And the effect of the surface roughness is basically the opposite to the effect of the thermal inertia. If we increase surface roughness, we increase the flux. And both, if we go back to the thermal models with the eta value, then these effects, kind of fight within each other and influence the eta. So basically, surface roughness decreases eta, and the thermal inertia, on the other hand, increases it. But also there is the influence of the shape, so it's much more complicated. Okay, before the actual thermophysical modeling, let's talk briefly about the input data. We use the the thermal fluxes from WISE satellite that was launched in 2009 and observed since January for almost 9 months in 4 filters, and detected a lot of asteroids, and only the data in 12 and 22 microns are dominated for main belt asteroids in general. In thermal, so for thermophysical modeling, we use only these 2 bands. And to get the data, we use the standard process described in several papers of the WISE team. So there is no magic. And the other input are the shape models, which are derived from the convex inversion of Mikko Kaustalainen. It's a convex polyhedron with rotational states, scattering parameters, and it's basically from only disk integrated data. And we use this model is basically the kind of best one we can get from only the disk integrated data, because in the disk integrated optical data there are very few signatures of the non-convexities. And the majority of the shape models are there's few hundreds of shape models based on convex shape models, and on the other hand, there are very few based on radar data or spacecraft. So this is something called classical TPM approach, where the TPM is basically a direct method where you choose your parameters and compute the temperature and input the fluxes, and then you compare them with the observations, and you construct basically chi-square. And this plot shows different behavior of the fit when we change the thermal inertia for different roughness. So it seems that, for example, the medium roughness seems to fit the data the best way for either, somewhere around thermal inertia of 100. And next, I will show you these kind of images, but mostly only the envelope of the best solution. So this is basically the same plot for 4 different asteroids. Here you see still Ivar, but there are other asteroids like Hector, which has very deep, and deep minimum near very low thermal inertia. And Karin and Odessa, they have also, relatively not that wide, or there is a prominent minimum in the thermal inertia. however, know that the reduced chi-square values are relatively large, so it seems that the fit is not perfect. Okay, there is just a short summary of the classical TPM approach, which is relatively fast, even for relatively complex shape models. It gives us more realistic sizes than the thermal models. However, they do not directly account for the uncertainty in the H and G values and the shape and rotational state. And the shape and rotational state we investigate. I will show you then if they are important or not. Also, we need to search in the finite grid of parameters, so there is no convergence in the parameters. And as I showed you, very often the chi-squares are not ideal ones, so it seems that the fitting has some caveats. And also, for this we require data from at least 2 filters. Okay, so the investigation of the importance of the shape was done by our method, where we use the optical data and bootstrap them, and then use the inversion to compute the shape model again. And this process gave us kind of similar global shape appearances. However, the shape models should map the uncertainty of the shape. So here you see IVER, but constructed from 6 different bootstrapped optical data sets. They look pretty similar. And if you look at the distribution of the spin axis within the varied shape models, or the models that are that corresponds to the bootstrap optical data, we generated for each asteroid 30 different shape models. Then you can see that also the uncertainty in the spin axis is kind of sampled. Sometimes it's larger, sometimes it's quite small. So, and then we basically had like 30 different shape models of the same asteroid, and we ran the TPM for each of them. And these are the results. The fifth line is the TPM with the original shape model, and these thin lines are for the varied shape models. And you see that for Hector, the solution is very consistent, or the solutions are consistent within each other, and we are even able to improve the fit. So some of the varied shape models fit the data better than the original one. Similar for IVER, but here you can already see that the thermal inertia values of 200 should still be acceptable, but they are not suggested by the original shape model. So the uncertain, or the range of the acceptable thermal inertia is underestimated when we use just the original shape model without accounting for the shape uncertainty. So these are 2 different examples where it works nicely, where the solutions for the thermal inertia are consistent within each other. But there are also cases where you get very different, quality of the fits. So you get TPM, or the best solution with one of the varied shape model can have chi-square of 15, but on the other hand, it's almost 1. So there is a big difference. However, as you can see here, that the minimum is always on the same place, which is nice, but it's not general. There are some cases where it's much more confusing, and you can see, for example, here that the nominal solution is somewhere around 200. Both solutions are consistent, but some of the varied shape models give you very low thermal inertials, which means that in reality, the thermal inertia should be, is not constrained, or it's probably between 0 and 300. And again, using only the shape model can bias the results. The original shape model can bias the results. So that was the part about the investigation of the uncertainty of the shape model, and just briefly about how we played with the WISE data. We basically used the properties of the survey, because WISE observed, the exposure times of the observation were 8 seconds, and 3 seconds there were the readout. So we have 11 seconds between 2 subsequently observed frames, and there is an overlap between the areas of the frames. So in principle, we can have observations of one particular asteroid separated by 11 seconds. So, and we found that for asteroids with convex shape models, there are about 400 such observations. And the change in the flux, just because of the orbital and rotational evolution, is like 2-3 orders of magnitude lower than the actual uncertainties of the fluxes. So it can be negligible, and in principle, these points can be used to independently estimate kind of the accuracy of the data. So we tested a simple hypothesis that we have these two double detections with fluxes F1 and error sigma 1 and F2 sigma 2, and we test the hypothesis that they are drawn from a normal distribution with a mean, mu, and the dispersion, corresponding dispersion. And the mu is, we assume that it is the same. Okay, so we constructed a quantity which is a difference between the fluxes, and it's normalized by the sum of the square roots of the dispersions. And this quantity should correspond to the normal distribution centered to 0 and with a dispersion of 1. So we computed this value for all the double detections for W3 data and W4 data, and created the histograms and fitted the normal distribution. And you see that it's not N01, but the dispersion is much larger. So it seems that the sigma 1 and sigma 2 are too low, and they should be increased by this factor and this factor to receive the something we can call sigma, the standard sigma errors. So we decided to apply to all the data, basically. And another thing is the Weiss-Spitzer cross-calibration reported in Jared, who studied about 20 K-stars and 1 galaxy near the ecliptic poles. And these areas were observed by Weiss basically constantly. So basically for the whole 9 months, they have observations of these objects, and they found out that internally these sources are the fluxes are internally stable within less than 1%. Actually, it's much less than 1% for each star. However, there is an ALMA scatter around the 0 value given by the Spitzer of 5% in both W3 and W4 filters when we look at individual objects. So it means that some of the star has a flux which is larger than should be because of compared to Spitzer, but some of the stars are fainter. But it's not clear it's not clear how it is for individual objects. So it's very difficult to tell that this asteroid is shifted this way or that way. And also this study was done for stars only, and there is a fundamental differences between the stars and asteroids. So we think that there might be something, but it's not clear how the asteroids are affected, because they are much brighter sources than the stars. They are variable, so the fluxes are changing rapidly. And also the temperature of the asteroids typically 200-300 K, but for the K stars it can be 3,000. So we just decided to kind of test this effect, which could cause the change between the bands, which is important for the time inertia. If you change the rate, the band rate, the band difference, you change the thermal inertia. So we decided to fix W3 and change shift W4 by ±10% within W3, and with a step of 2%. And the red line is the original, the fit with the original data, and then the blue ones are fits with the shifted W4 data. You see that there is some influence, that the minimum is moving, but it seems that it's not that much. Okay, so I can leave you with the conclusions. The main one is that probably one should try to estimate how the uncertainty in the shape model affects his thermophysical properties. Thanks. Thank you.
Could you tell whether the biggest difference in the when you were fitting with different shapes and spin pole orientation, whether the shape was more important or the spin pole orientation was more important?
I cannot distinguish between them.
Okay.
I don't know, but mostly the change in the pole orientation was quite small, so I guess it's probably more the shape.
Good question. I think it's a very good, important question. Migo? I suspected a question from Migo.
This is great. You could probably even turn this around, saying that when you get different fits, but some have a much better chi-square than others, you can use the thermal data to reject some shape models that would be allowed by the optical data. It's kind of in the same spirit as what we heard earlier today.
In principle, yes. So one can try to use the thermal data together to make the shape better, which will be shown by Joseph in his Friday's talk at the end of our meeting. I think Ben was trying to ask.
Yeah, Ben.
Yeah, hello. Again, this is nice work. So my question is, so you got original shape model and you fit the thermal data with it, you get a poor fit. And then you try to improve the shape model using your bootstrap method, and you still get a poor fit. Would that then lead you to imply that there's like a varying thermal properties across the surface? Because I guess you're still assuming an average thermal inertia across the surface.
I think the main problem could be the assumption of the convexity.
Okay.
I think if you make the shape model more realistic, like maybe the poor fits tell us that the object is more non-convex, or that is messing with the solution because of the non-convexity.
More questions? No? Okay, so thank you, Joseph, again. And we move to the next talk that is, I think, is about. Right. So next talk is by Max.
No, you give them to them.
Right.
Okay, so it's not the same system. Can you use your? Maybe you want to use your computer. Okay.
Okay, we have a technical again little problems. So we're using.
No.
No. Right. So.
Because
okay.
Not connected.
Okay. So Max Devogele is going to talk about the how can we find or how can we determine the amount of concavities in convex shape models derived from light curve. And I think this could be very interesting for TPMs, as this is linked to a question from Ben.
Yes, yes. Yeah. The keys. And this is the content.
Okay, thank you, Max.
Okay, so hello everyone. So I will speak you about methods like Marco said to search for large-scale concavities in asteroid shape models. So this work was motivated first by the discovery of the strange polarization of the asteroid Barbara. Paolo will talk you more about these Barbarian asteroids, but mostly most asteroids have certain properties when you observe them in polarizations, like Alberto already told you about. So in low phase angle, you observe negative polarizations, and with an inversion angle around 20 degrees. In the case of Barbara here, you can see that the inversion angles is around 30 degrees. So the reason for this large inversion angle is still unknown, but some assumptions were made to explain this wide inversion angles. And one of these assumptions was that maybe large-scale concavities may play a role in the polarimetric observations. So in 2008, new barbarians were found. And so you can see here a nice plot of all the polarimetric observation of the barbarians. And you can clearly see that you observe a different kind of polarimetric phase curve with an inversion angle here around 30 degrees, while normal asteroids have an inversion angle around 20 degrees here. So since this discovery in 2006, the asteroid Barbara was widely observed, and non-convex inversion was possible using the koala algorithm. And you can see that, as it was suggested, that concavities may play a role. In the case of Barbara, we found several large-scale concavities on the non-convex shape model. So, but with only one non-convex shape model for barbarians, it's not possible to make the link between the concavities and the polarimetric response. So other non-convex shape models of barbarians are needed. The best method to obtain shape models is, of course, the live curve inversions, but the classic live curve inversion is known to be unique only if the model that you use to model the asteroid is convex. So no information about the concavities normally can be retrieved with only normal live curve inversions. In order to obtain a non-convex shape models, you need to have additional constraints like stellar occultations, static optics, and interface measurements, like some person told you about before. So the koala algorithm is able to take all these informations into account, and the example is Barbara that I showed you before. But The non-convex inversion is only feasible for only a few asteroids, mainly because, for example, for occultations, the occultation are quite rare for one specific asteroid, and it needs a lot of manpower in order to obtain a very good result. So very few solar occultations are available for barbarian asteroids, and for example, for the other two techniques, they are only feasible for the biggest and brightest asteroids. So they are not feasible for other barbarians like asteroids. So we may wonder if the informations about the concavities are totally lost in the classic convex inversions, or if there is a way somehow to find their presence, if they can be retrieved on the convex shape model. So in 2001, in the work of Casalainen and Torpa, they used non-convex shape model in order to simulate some life curve, and they introduced this life curve inside their convex inversion, their life curve inversion curve. The results that they obtained, they see that the shape model that they obtained, the convex shape models here, it's always very similar to the convex hull. And the convex hull is simply the minimal volume, which will enclose the original non-convex body. And one of the properties of the convex hull is that it will tend to fill the concavities with large flat surfaces. So this was said in the work of Casalainen and Torpa, but it wasn't never studied to see if the flat surfaces that we found on the convex shape model can be because of the presence of concavities or not. So yes, maybe life curve inversion can give us information about the locations and the extension of concavities, but no information can be obtained about the depth of these concavities. We only know their location. So first, what is a shape model? Simply, quickly, so a shape model is a set of points that we call vertices. And we will make a set of a combination of 3 vertices to make the triangular facets. And you can see here an example with the vertices and the facets. So the methodology of our methods to detect the flat surfaces. First, we compute the normal of each triangular facet of the shape models that we want to analyze. Then we project the direction of this normal of the facet over the unit 2 sphere. So you have here one example of a convex shape model. And here you can see the projection of the normal direction on the sphere with the red dots. Then we subdivide this sphere here into n bins with almost equal areas. So you can see here the subdivisions in the triangles which are tilling the sphere. Then we sum the area of all the facets which bins are falling into a specific bin. For example, if we take that bin specifically, we'll sum the area of all the facets which are here. So we have like 4 facets which are falling into this bin. So first this bin, we sum the area of all these facets. So here you have a plot with the 320 bins that we use in that particular case. And here you have the cumulative area that are in the bins. This cumulative area is normalized by the total area of the shape model. And you can see here that in that specific case, which is a convex shape model, which is not presenting any evidence of a flat surface, the maximum cumulative area is around 1%. But now, if you take a different kind of shape model, like this one, which actually is resulting from the convex hull of a priori convex shape model, and you can see now that the presence of large flat surfaces like here and here, and you can see here on the projections on the sphere a clear difference. Here the points are well spread over the sphere, and here you can see some concentrations which are due to the flat surfaces on the shape model. So if we take again this kind of plot, you can see here the plot again for this example, and here for that one. You can see clearly the differences. Now here the maximum cumulative area that for bin is 4%. So the last step of our method is to determine a threshold, which will we use in order to determine if the bins contain a flat surface or not. And after some simulations, we found that for the case with 320 bins, the best threshold is around 2%. You can see here that you have some bins which are containing surfaces higher than 2%, and in that particular case, you don't have any flat surfaces. So the method contains 2 parameters that need to be adjusted. As I said, you have the number of bins, which will control the flatness tolerance that you accept for the detection of a flat surface. It can be seen simply because if you have a great number of bins, these bins will substance a small solid angle. So in order to have 2 bins to fall into the 2 normals to fall into the same bins, you will have a small angle between them. And the other way around, if you have a small number of bins. And the detection threshold simply controls the minimal size that you can detect. So here is an example of the application of this method. We tested on the shape of 433 Eros, which is well known by spacecraft observations. So you have here the non-convex shape models, and you can see clearly here the concavities. We computed the convex hull of these shape models, and you can see here the flat surfaces induced by the computation of the convex hull. And then we applied our method on this shape, and you can see here the locations where the flat surfaces were found. So you can see that these locations correspond very well with the location of concavities. But in that case, we took the convex hull, so it's maybe quite easy. It's a perfect world. But we also tried on the non-convex shape model obtained by means of live Fourier inversion. So this was possible for Eros. So here is the results of the convex inversions. We can see that it's quite similar to the convex hull, but not the same. And we applied our method to this shape model. And the result is here. So the concavities are still, we can still find the concavities with maybe some displacements like here. The true concavities is here, but still the concavities is detected. And you can see here the differences between these 2 models. So the main concavities is still well detected, and here we detect the other large concavity. So then we introduce a parameter which can give us an information about the degree of the non-convexity of a non-convex model. So we call this parameter the volume ratio, and these parameters have 2 parameters, which is the volume of the non-convex shape models and the volume of the convex hull of this non-convex shape model. So we can compute here the volume ratio, and this volume ratio will have a value of 0 if the convex shape, the shape is convex, because the convex hull will be exactly the same as the original shape. So this will be 0. And if the shape model contains some concavities, it will be between 0 and 1. More closer to 1, because 0 is quite impossible, but there is no clear lower value. So then we did some numerical tests, and we took a set of non-convex randomly generated non-convex shape models. We computed the convex hull for these shape models and then the volume ratio. And for these same shape models, we simulated life curve that we put inside the life curve inversion programs. And then we applied our methods on the results on the convex shape, which is resulting from life curve inversion. And so here you have the result of this numerical test. Here you have the volume ratio for these non-convex shape models. And here the fraction of flat surfaces that were found on the result of the life curve inversion. The fraction of flat surfaces, it's actually simply the sum of all the flat surfaces that were found on the convex shape model. What you can see here, the result of the simulation in the black dots, is that we can see a trend which we fit it with power law. And in order to see if this trend still exists in the case of real asteroids, if our simulations produce asteroids-like shape, we also computed the location of this graph for asteroids which well-known non-convex shape, like Eros and Cleopatra here. So for this one, we could compute the volume ratio, and we also have life curve inversions using only the information of the life curve. So we obtain a convex shape models with life curve inversion. And you can see that all these asteroids fell well within the error bars of our fit to the simulation. So we can obtain a qualitative idea of the abundance of the concavities on the non-convex shape models. For example, here for 2 Pallas, we can see that the fraction of flat surfaces is near to 0. So we know that it should be convex. In the case of Cleopatra here, we can see that it's a very irregular object, and we know that it is. So in conclusion, a new method that allows to infer the presence of concavities has been developed. The first test seen on Wenlow asteroids seems to produce good results, and a paper was submitted about this rock last month. So in the future work, we plan to apply our method to all available convex shape model and try to cross-correlate the results of these methods with polarimetry and TPM, for example, in order to check if the concavities play a big role in these techniques or not. Because most of the time, the concavities are neglected. So thank you for your attention.
Thank you. Questions?
I think that you would save some time and effort if you worked in the Gaussian image space, because it seems to me that because the output of convex inversion is this Gaussian image that then you convert to.
Yeah, we thought about that, but maybe we can try also to do it directly on the because it was maybe easier with the simulations when we simulate non-convex shape models. We have it directly on the normal we don't have in that particular space. So, but maybe we may convert them into that space after. But
have you looked at the paper by Torpa et al. From 2008, I guess? She did similar things.
No, I don't know about this paper.
It's very, very similar kind of way.
Okay.
More questions, George?
So, I mean, one really interesting thing about the barbarians is that they have this unique spectral shape, the unique composition, the very CAI rich.
Yeah.
Is that at all something that could affect the polarization inversion angle?
Yeah, we think that it's the main reasons for the polarimetry, but maybe it's also related to the presence of concavities, because we think that these asteroids are quite old. So if they are old, they may suffer some collisions which will create these concavities. So it's not a direct, maybe it's not a direct relations, but still there is.
Thanks.
More questions?
One of the major sources of concavities are impacts.
Yeah.
And we know pretty well how crater shapes look. Would that improve your future analysis if you?
Yeah, I don't know, because the impacts are maybe low scale. So here we are searching for very large scale concavities, because the light curve inversion will not give us information about the small craters. So when the shape, I think, of the crater is big enough, we may lose this relationship.
Well, if we're talking about asteroids on the order of a few hundred kilometers, they are most likely having craters of that size, 50, 100 kilometers. So
Okay.
this is exactly the.
So maybe
the
yeah,
size
for the
range.
largest asteroids, we can obtain a better information about the concavities, and maybe retrieve like the depth of the concavities.
I have a related question. So, are C types have more concavities than S types, or it's too early to say?
I don't know. I didn't check we only did the numerical test, and we still didn't apply to all the step models, so we don't know.
I think an ideal target to consider is 2,253 Matilde, for which we have very large and deep also craters, concavities.
More questions? No more questions? So, time for lunch. We had lunch together. The first